Okay, so I'm just going to get started here. Um, yeah, so once we've done, um, so once you've input all your data into ACP, you want to go into static structural. So static structural basically does the mechanical analysis for you, inputs all the forces, the fixed points, and from there we'll evaluate the results and then um, output output the results in a meaningful manner so that you can look at it and be like, okay, does it fail? Does it not fail? Does it meet the constraints that I have? So coming up with the constraints, it's up to you as a designer. The constraints mainly focus on things such as to do with the driver. It has to be really stiff. So deformation has to be like less than an inch. So and things like the steering wheel should definitely be like super stiff, like so less than a millimeter of deformation when at max loading. So this is because so think about it. If you're driving a car, you don't want your steering wheel flopping around or like having some give, or your seat moving around and flexing underneath you while you drive. So because of that, you have to like carefully consider like the deformation. Certain things like um, the the front wings, they will also have a certain amount of deformation, um, like based on rule compliance. So you'd have to look up like the various rules and see what they say about how much deformation is allowable. Um, and then number two is also you think about factor of safety. So generally, I go with a factor of safety of 2.5. So how I arrive at that number is for formula stuff. Um, Typical metal materials like metal structures have a factor of safety of 1.5. So which means that for the max loading that a part is going to see, um, so in order to meet the max loading that a part is going to experience, just just meet that spec is a factor of safety of 1. So that means if we go slightly above it, it's going to fail immediately. A factor of safety 1.5 means that the part can safely take about 1.5 times the max loading before failing. Um, and then you add another knockdown factor of 1. So the end result is your factor of safety will be 2.5. So the knockdown factor comes into play with carbon fiber because due to manufacturing defects. So, for example, someone messed up the fire orientation by like a few degrees, and because of that, you don't know what's going to happen. Or a random piece of material like peel ply got stuck in the middle of the carbon fiber, or there's a random void that appeared while laying up. So, because of all of this, you should aim for a factor of safety of 2.5 at least, right? So those are the three things that you usually have to think about. Deformation, two things, deformation and factor of safety. So yeah, so once you're done with ACP, so before, I don't know whether you remember this, but before there was a solid model, like the part that I showed was the thickness part of it. So I was doing some research about it and I realized that ACP will automatically transfer a solid model if you have plies of different thicknesses um, throughout the thing. So for example, remember last time we had sorry. So so remember last time we had the side panels having thickness of 6 plies, whereas the center panel was 3 plies. So because of that, ANSYS would automatically, because of the difference in thicknesses, ANSYS was not able to produce a shell model. So that's my bad. I forgot about that. So if you want a shell model, you have to make sure that the thickness throughout the entire part is uniform. If not, you have to use a solid model, which is not much of a big deal. But yeah, more or less the same thing. So for simplicity's sake, I went back and I converted everything to the same thickness. And yeah, and then I opened up. So everything's now 3-ply, and this is the. And once you click on static structural, damn it. So once you click on static structural, you click on model, it will open up this thing, and then you'll see that under here you'll see there's a mesh, imported plies. So if you open that up, you'll see ACP pre, and underneath that it'll put all the settings that you input under ACB pre. So usually you don't have to care about all of this stuff. The only thing you have to worry about is static structural. So under static structural is where you input all the all the load cases. So first, before we do anything for composites, before we put any load cases, you want to put under solution. You want to ensure that you insert solution. Under solution information, you want to insert where is it? Yeah, okay. So under solution, yeah, I was right. Okay, under solution, you want to insert composites, and then you want to put composites failure tool. So under composites failure, there are usually different schools of different ways that you can analyze failure within composites. So there are three main schools of failure, composite failure. So first is maximum strain. That means for a given ply, there is a certain amount of deformation before the ply will fail. Then there's maximum stress, which means there's a certain amount of stress that the ply can see before it fails. And then psi wu, which is a combination of both. And honestly, in my opinion, is the best way of analyzing failure. But for safety's sake, so in order to select these, you need to go into composite failure tool, and then under reference, you need to reinforced ply criteria. You need to choose to turn on maximum strain, maximum stress, and psi wu. Everything else you can just leave alone. So as you can see, there's like tons of other failure criteria. You don't just ignore that. Just as long as you select these three, and if the ply fails based on any of these three criterions, it will tell you, just to cover all bases. So once you're done with that, you can go ahead and open up the composite failure tool, expand the tree, and then you'll see the inverse reserve factor. This means that for as long as the number is below 1, that means you're good to go. And if it's above 1, it means it's going to fail. I don't like this because it's very hard to tell, and also it doesn't give you like in terms of factor of safety, then you have to go an inverse factor of safety. So 1 over 2.5 just it's not nice. So you want to open up, you want to right click composite failure tool, insert, and then you want to put in safety factor. So this will output your factor of safety so that you can see it and make sure that everything is above 2.5. All right. So once you're done with that, you're done with composite failure tool. Now you want to input the loading cases. So first is you want to put standard earth gravity. So goes without saying, like, yeah, everything has gravity. So so it'll ask you what direction. Just have to put in negative y direction because most of the things, like based on however you want to see it, but like how the part will be oriented in real life. Because it's a flat panel, I'm assuming that it's going to be held like horizontally, and you're going to be applying a load this way. So obviously it's going to be negative y direction. So once you're done with standard earth gravity, you want to put in fixed support. So under here, so as you can see, there's like a whole list of other supports that you can use, but for simplistic, you can use fixed support, right? And then under geometry, it'll be automatically highlighted. You just, so remember in the earlier part, we split the body up while we were first processing the stuff. This is where you use the split parts. So in this case, I want to select the areas which I know will be selected. So for example, I have a tab that is going to be bolted to this. So let's say the square tab, and it's going to be bolted to the composite, to the flat panel. Generally, the whole area is more or less like a fixed support because it can't really move, and I'm assuming that the metal doesn't yield at all, which is a valid assumption, assuming that you also carry out FEA on the tab and make sure that it can take the loading that you intend to place on this. So for example, if I'm intending to place like center loaded, then the load, like let's say I'm planning to put 100 newtons on the center of this part, that 100 newtons will be evenly distributed between the floor. of course, sometimes it's like then there's also need to take into account the moment about that the load. So just remember that when you do FEA analysis, right? That you need to make sure the tabs also will not yield. Yeah. Okay. So once you've selected all four, so I basically held down Control, and then I just selected on the four corners. I click Apply, and then it'll automatically turn like purple, blue, yeah, whatever. And then that's basically a fixed support. Um, so uh, so with FEA, you need to always remember to put your fixed support. These are known as your boundary conditions, which just basically means that when you resolve, like in order for FEA to solve itself, it needs to be able to know that um, that you that there is a node at which there's a zero, like all the constraints are known. So, i.e., the deformation and the stress that it will experience are known. So that's where your fixed support comes in. And yeah, it's if you don't have your fixed support, the item cannot solve itself, because essentially, think about it. If something is floating in space, and then you apply a force to it, it's just going to keep going. Yeah, and it might oscillate, it might resonate. There's like a bunch of things. So yeah. So usually in the case of automotive industry, you need fixed supports to as your boundary condition. There are other ways to solve it, like so for example, you use inertia, but that tends to be with aircraft systems. But we're not going to go into that. All right. So once you have fixed supports, next you want to do is put your force down. So I'm just going to create another force. So obviously there's other things like pressure force, remote force. But yeah, I'll leave you to explore what those mean. Like you can generally like Google it and figure out what you think is necessary. But generally, I just apply a force, and that's pretty good enough. All right. So then under force, you can define it. There's two ways you can do it. So geometry, you want to click and then apply. So it's pretty much same as the fixed support, but the only difference now is that you need to define how much force is, how the force is being applied. So so let's say so there are two ways to do this. One is you can use a vector. So what that means is that the force will be applied perpendicular to this space. So for example, if I put 100 newtons here, you can see that there is a red arrow that comes pointing out perpendicular to it. So I can change the force. Yeah, but I generally don't like this. Yeah, I prefer to use what's it called? Component. And then under the component, I'm able to choose whether I want to put it in the X, Y, or Z direction. So for example, if I want to put in the -100 in the negative Y direction, I just put -100, and then I'll see the arrow point downwards, and that's good. I just generally prefer to have it defined by components because it's easier, and that way I can find a control which direction the force is going. So for example, if I want to put a 45-degree force, then I can put like 100 newtons in the X direction as well, and then it goes in the 100 newtons direction. So yeah, so you can based on vectors, it's a bit easier to direct the force. Yeah, in my opinion. All right. So once you're done with that, you're done basically with inputting your. So that's just basically how you put your forces. So for example, if I also want to put a pressure, I can. So let's say I want to put pressure on this space here, and then yeah, so pressure, you don't have a direction because it's surface effect. So basically across the entire surface, there's going to be a constant pressure being applied to it that's always going to be perpendicular to the surface. So let's say I want to put 100 pascals, and then geometry, I just want to click apply, and then yeah, so you can see it's perpendicular to the force. So and then if you want it on the other side, you have to go flip it on the other side and just apply that. But yeah, so those generally are the two most common used things for formula. You don't really need all that. Okay, so I'm going to reduce this. Okay, yes, I'm going to delete this object. All right. So once you're done with that, you want to go on to solution, and then you want to insert. So let's say, remember how I said deformation is important? So directional is important, but usually I go with total deformation because then it just shows how much deformation is occurring throughout the entire thing. Because usually you're not going for directional deformation, you're usually going for total deformation. So any deformation is bad when it comes to driver requirements or rule requirements. So usually just stick with total deformation and that's good. So once you're done with total deformation, that's pretty much it. And then you want to put, let's say, you want to put equivalent von Mises strain, or actually no, sorry, stress. Yeah, equivalent von Mises stress, or you can put maximum principal stress. So maximum principal stress just means at a point how much stress is being applied, and equivalent von Mises is like it also takes into account the deformation and how the stress is being distributed. There's a formula that you'll learn in 156A if you ever take it. But usually equivalent von Mises stress is pretty good for me to see how much, yeah. But I don't look at stress usually. I only look at factor of safety as well as my total deformation. These two are the most applicable to the case of composites. But yeah, okay. So once you're done with all of that, just go up here and click solve. Oh wait, sorry, I forgot to select what's going on here. Oh, sorry. So when you click equivalent stress, you need to choose layer. So then I'll just select the entire section. Yeah, okay, that's the issue. I forgot about that. But yeah, so once you click solve, it'll just run the calculations for you, and then voila, you have everything. So first thing you need to check for, so this is the equivalent stress. Okay. All right. So I don't care about equivalent stress. So remember how I say reverse factor is useless? So basically, yeah, you just see 0.04 and you're just like, what does that number mean? But if you look at factor of safety, you can see that most of the numbers. So first you want to go and look at here and see the color gradient. So it will usually say 20, it will say a number given by min. If it's below 1, it will highlight in red, it means really bad. And then, so in this case, I have a factor of safety of 24.017 minimum across the entire thing, which means that this part is ridiculously overbuilt for the amount of load it's going to see. But then that's not the only thing, right? Like we'll also have to look at deformation. So if I look at deformation, maximum deformation is, oh yeah, okay. So it's 2 times 10 to the power minus 5 meters. So that's like, what's after millimeter? Nanometer? No, that's times 10 to the power minus 9. But yeah, it's ridiculously small. It's halfway between a millimeter and a nanometer. So that means this part is once again ridiculously overbuilt for what you expect to see. But yeah, sometimes it's good to have overbuilt parts, especially if this entire piece is only 3 plies, and it's only being applied 100 Newton force with all these deformation, like it's okay. Like 3 plies is negligible. We're not like a Formula One team that has to shave grams off. We're just, yeah, carbon fibers, like, yeah, cheap for a 3-ply piece, so we can do that. Yeah. The only issue comes in when you're doing something with like a seat, and you find the plies going up to like 12, 15, 18 plies. Then that's where the issues tend to come in, because number one, you also need to consider that you are going to be putting down each of these plies, and anything above 8 plies can get very tiring. And very long time consuming. And also, the more plies you have, the more risk of defect you are at. So generally try and keep everything below 12 plies. I find that's the sweet spot. Um, and yeah, and as much as possible, try and reduce the thing. All right, so that's pretty much it for ACP. All right. Yeah, any questions? Okay, then I guess, yeah, then I'm done for this stuff for this week. So what I would like you guys to do is, if you have time over the next week or so, go and try and make your own flat panel, figure out how to mount it, see how much force it takes to get, like what's the max force um, a flat panel can take. So the requirements are it should be within 10 millimeters of deformation and a factor of safety of 2.5. All right, so see how many plies you can take. So let me type it out. Make sure that okay. So first, so let's say you have 100, let's say, okay, 5,000 Newton force. Okay, 5,000 Newton force, a flat panel of 50 centimeters by 50 centimeters, and see how many plies you need. Okay, so this will be like your sort of rough um, guide. So if you have any questions about this is generally like super simple. It's just more for you to reinforce the ideas and give yourself practice on how to do the flat panel, like how to walk yourself through the ACP. So yeah, so I'm just gonna go through a simple recap of what it takes to get to this point, right? So first, entering data, you go in there, you input all your carbon fiber material properties. Once you're done with that, you drag in a mechanical model onto the tree connected to your engineering data. And then under geometry, import your SolidWorks model. So how you do it, you just right click it and just click import geometry, and then click browse, find the geometry, import it in, and then process it in SpaceClaim. So in SpaceClaim, you first have to get all the surfaces out of the model. So basically, like what surface you're going to be building out of or into. And then you want to split the model up. So for example, if you're mounting it at a certain part, you want to split around that circle. And then after you're done importing that after you're done splitting up the model, you want to connect that model into your ACP pre. So once you have the model, go into setup and and then in model, after you're done with processing in SpaceClaim, you need to go into model and then mesh it. So meshing, is you do a face element size, make the mounting holes, like the areas where it's going to be mounted super fine and mesh compared to the rest of the mesh, um, and and then once you're done with that, import it into your ACP pre, set up the model. So basically define your carbon fiber stack up, put your stack up wherever it needs to go. And then once you're done with the setup, then you need to put into static structural, define your forces, your boundary conditions, and then run your results. And then see what your factor of safety is, see where deformation is. And from there, and then if you're not happy with the results, repeat steps from your ACP pre to static structural again. So basically, like import more plies into your stack up, or if not, reduce the number of plies in your stack up. Yeah, and that will usually get what you need. All right. Okay. Any questions? All right. If not, I think we are good. Then next week we'll have another short lesson on meshing. So a bit more detail on meshing, as well as what's the other thing? Ah, yeah, name selections. So how would you define like a draped carbon fiber? Right? Okay. If not, I'll see you guys next week. Just practice with ACP. Right? All right. See you guys. Bye.